Next on our list, let's see here. We have ASICS for cryptocurrency, benefits and challenges by AVNet.
Okay, hello everybody. My name is Pavel Vilk and I'm an engineering director in AVNet ASIC solution. I will present today a presentation regarding challenges for ASIC development for cryptocurrency markets. So first of all, a few words regarding the AVNet. AVNet is the biggest distributor of electronic components in the world. It has more than 50,000 employees, more than 2,500 engineers. It provides more than 122 billion shipments in the whole world and has more than 1 million customers. We are AVNet ASIC Solutions division inside the AVNet. We develop custom ASIC solutions for our customers. So you can treat us as a one-stop shop when the customers can come to us with idea, specifications, and we will develop for him an ASIC solutions, and eventually he will receive a tested, characterized, and working chip. And afterwards, we will manage for him a logistics, manufacture, and the production line. So we are working, we are agnostic technology solution. So we are working with different foundries. Based on customers' requirements and needs, we will identify for him the best technology nodes, and we are working with the biggest foundries like Global Foundries, TSMC, and Samsung. Okay, so here you can see some examples of cryptocurrency projects that we have done. On the left side is Spondulis SP36. This is an ASIC for cryptocurrency market, and its performance more than 600 gigahash per second. And currently, this is the best X11 algorithm crypto miner in the world. On the left side, you can see an example of the ASIC that we developed for the Bitcoin applications 1 year ago. It was done on the Samsung 10 nanometer technology. And for the time, it has a very good parameters, 150 gigahash per second and 65 to 75 milliwatt per gigahash. 1 year ago, it was quite good. So what are your options? So you can go for the standard solution based on the standard components on FPGA, or you can go for the customs when you can optimize performance, area, and power. In that case, if you decide to develop an ASIC, custom ASICs, the pros are very clear. You can manage your supply chain and control the vendors. You will get a cost-plus model versus market price, and you can control the allocations of the specific chips. On the other side, you will need to pay NRE, the price for the development, IPs, for the masks, tooling, and etc. And you will have time to market, development, and bring up cycle. And of course, there is a risk of development of the new product. In any case, you need every time to consider ROI, return on an investment. So you're probably familiar with the internet calculator for the Bitcoin, when you can see the hashing power, the power consumption, and the cost per kilowatt. And in that way, you usually calculate if it's profitable or not to use a Bitcoin ASIC. In case of the developing your own ASIC, you need to take in account except the hashing power and the power consumption, also time to market and ASIC cost, which include an array. So when you calculate the ASIC unit cost, you will get the number of the dice from the wafer. On top of it, you will need to add the package cost and the test cost, and there is production yield, because not all the dice will come as a good dice out of the foundry. An array is one-time payment that you will pay for the development cycle for the different tools, implementation, packaging, prototyping, testing hardware, emulation, and other topics. Okay, so when you decide to do the ASICs, you need to consider the following. You need to define the silicon process, choose the silicon node, foundry, and the flavor, what kind of the libraries you want to use. and based on that decision, you will get the voltage, the working voltage, max frequency, and the power consumption. And the next very important step for the ASIC is to optimize the power, both dynamic and static. So now I will go through the specific example of the Bitcoin and see how we can optimize the power and what can have a big impact on the power optimization. So the SHA-256 is a very straightforward algorithm, and it's not allow you to optimize it in very sophisticated ways. Of course, you can add some features like ASIC boost, do some rounding, and use constant numbers, but it will not save too much power. Another thing that define SHA-256 is the fact that you do not need memories. In the contrast to Ethereum or other cryptocurrencies, you're based only on the sequential logic and combination logics. And this is why ASIC is so popular for the Bitcoin, because you can insert logic elements as much as possible inside the die. So when we look on the power consumption, it's important to divide power consumption for two types. The first type is dynamic power consumptions. It happens when the transistor switching. It depends on the clock frequency. And the formula for that is very simple. Power is activity multiplied by capacitance, multiplied by voltage quadratic, and multiplied by frequency. On the other side, there is a static power. The static power exists all the time. It's so-called leakage power, and it doesn't matter if transistor works or doesn't work. It doesn't depend on the frequency. And it's heavily depend on the voltage, on the process, and the temperature. It's very important to understand that there is here a positive feedback effect, that if you increase the efficiency of the ASIC, the temperature goes high, the leakage increase, the power increase, and then temperature goes high again, and then the leakage increase, and eventually you can get a thermal runaway. So when we analyze the dynamic power for each of the elements which exist inside the formula, we can see if it depends on power linear or quadratic, and how we can solve in order to reduce these factors. So for example, for the capacitance, of course, we can go to most advanced nodes like 22, 16, 14, up to 5 nanometers. Or we can do the custom design or use special libraries or manual layout in order to reduce the total capacitance inside the circuit. For the voltage, of course, and since power depends on it in the quadratic way, we can reduce voltage at least up to 0.3 volt. We can use very special transistors with ultra low level threshold, and we can do silicon binding in order to find chips that will work on the lower voltage. The same is for frequency. Of course, if we go to more advanced nodes, we can get more frequency. We can do the custom design in order to improve the frequency, and we can do silicon binning. And for the activity, we need to optimize algorithm. As I mentioned, for the Bitcoin algorithm, there are not so much to do, so we can do either ASIC boost or some round optimization and other very well-known features. Okay, a few words regarding silicon process variations. So you need to know that when you receive chips and when you manufacture in the big quantities, all the dies will be different. The difference in between the dies will be not only between different lots and not only between different wafers, but it can happen also inside the wafer, and also transistor inside the die can behave differently. For that, there is a so-called Gaussian distribution. And if you look on the left corner, there is a graph that displays for you. So vertically, you see the PMOS transistor, horizontally NMOS transistor, and you can see that the upper right corner is so-called slow. Well, both transistors are slow. So in that case, the frequency will be very low. And the lower left side is fast corner when both transistors are fast. And in that case, you can run faster, but the leakage will be very high. And all the variation of the transistor will be inside this circle. So it's important to characterize and understand the boundaries of the circle. Now, let's look on some graphs and see what we can get when we have a dependency on the PVT. PVT is process, voltage, and temperature. So here you can see the examples of the transistors on the 10 nanometer technology, when you can see the dependency on the temperature and on the voltage. Of course, you see that the transistors which have work on the higher voltage will get a higher speed. And you can see also very interesting effect that as long as temperature going high, you can also increase the speed of the transistors. There is also here two types of the transistors. One is ultra low VT with very low threshold, and another is what is called LVT with simple low threshold. And you can see that ULVT transistors are much faster. So if you look only at that graph, we can say, okay, I can use only ULVT transistors and I can increase the temperature and get more performance. So why nobody is doing it? We will see it later. So on the left side is typical process and on the right side is slow process. And you can see the difference in the frequency. So the slow process is almost twice time is slower than the typical process. Okay, here's the example of and how we can play with activity. So this is dynamic simulations inside the SHA-256 and resolutions in the picoseconds, and the cycle here is 600 megahertz. You can see that you see almost the same graph. Nothing is changed. It means that SHA-256 is always working. You almost do not have any time that is not active. Therefore, you need to see how you can optimize it. So on the upper side, you can see SHA without ASIC boost, and below you can see with ASIC boost. And you see that on dynamic peaks, you have the advantage of 20% for the ASIC boost. And when the SHA is not active, you get the same power for the ASIC boost, with ASIC boost or without ASIC boost. So this is a small manipulation that you can do on the activity. But again, the main conclusion that we see here, the ASIC Bitcoin and SHA-256 will always work. Okay, so if you remember previously we saw how the temperature and process and voltage affect the frequency. Here you can see how the temperature, voltage, and process affect the static current and the leakage current. You see here on the left side, you see the typical process 0.35 volt, and on the right side you can see it for the 0.45 volt. In both cases, you see that leakage will increase almost exponentially as dependency on the temperature. So that's why it's not recommended to heat up. This is why you will get a thermal run effect. Because once the temperature inside the ASIC will increase up to 100 degrees or 120 degrees, you will get 3 or 4 times bigger the static current, and it will dominate over the dynamic power. On the other side, as we remember, frequency is going high or the deep nanometer process when we increase its temperature. So it's important to find some balance point when we can work around 50 or 60 degrees, when the static current is not too high and we still can run in the higher frequency. Okay, so just to summarize what we spoke before and what is important features to have inside the ASIC when we're talking about the Bitcoin applications. So first of all, its ability to work on low voltage up to 0.3 volts. We need to support wide voltage ranges because in some cases we want to run slow process on a higher voltage and fast process we want to write on the lower voltage. We need to have dynamic frequency control and automatically update the clock frequency depends on the temperature inside the die and depends on environmental conditions like voltage and the temperature. Of course, we need a temperature sensor for monitoring and overheating protections. We need ability to turn off each Bitcoin agent, because inside the ASIC there are many Bitcoin agents, and you want to control each of them independently if something's going wrong with them. Automatic adjustment of optimal frequency, as I mentioned before. We need a non-volatile memory, like if you to keep some parameters from binning or some other key parameters inside the ASIC in order to know different flavor of each chip. And we need, if we make a quite big ASIC, so we want to have separate frequency from control for the different areas inside the chip in order to optimize the performance. We need ability to turn on or off special features like ASIC boost, but we need to implement it in such way that it will not affect area of the die, it will not get an increase. And we need some bypass mechanism inside the chip in order to have a stable yield production and manufacture and always get the optimum performance from the chip. Thank you very much.